Okay, the next thing we're going to do, it's kind of a standalone theorem that we don't really have a lot of use for today, but it's a huge building block in what we're going to do next semester. In fact, it's the key step in proving L'Hopital's rule using this next theorem, which is part of the reason why we don't do that earlier, because it's impossible to do without the next thing. It's something called the mean value theorem. Now, there's two versions of the mean value theorem. There's the mean value theorem for derivatives, which is what we're going to do today, and then the evil version that we're going to do later when we cross over to the dark side, right? Which I think is next week, by the way. Right? Halfway through the semester, you guys know what the dark side is, right? That's when we do the anti-derivatives. Yeah. So we're all dressed in black every day and put on Darth Vader masks and stuff like that. Anyway, so the mean value theorem, I like to call it the rolling ruler theorem. So how many have ever taken a drafting class? I mean, I took one in high school. I don't remember why. I think I just had some time and it was interesting. And when you're drafting, you're drawing pictures of houses and walls and things. And it's really difficult to try to draw parallel lines. I mean, think about that freehanding. I want you to draw a perfect square without a ruler or without any lined paper. That would be difficult. Do you agree? Yeah. So you had what's called a rolling ruler. It was actually a ruler that would go up and down so you could easily create parallel lines. It was a convenience tool. So this is what the mean value theorem of derivatives kind of says loosely. I'll go through all the conditions. But I have some function that's going to have a starting and an ending point. Let's just say from there to there. I'll go over the conditions in a moment, but let's suppose it's just some happy curve. No weirdness going on. Now, I want to draw the secant between the endpoints. Okay? I can easily tell you the slope of that, right? That's just change of y over change of x. This is literally pre-algebra, right? Difference in the y coordinates divided by difference in the x coordinates. Now, imagine that this is my ruler. I would like to know, are there any places on the curve where the tangent line is parallel to this? Because that's what the rolling ruler is designed to do, is to create parallel lines. So if I did this, I didn't realize I had a ruler here. So if I did this, maybe about right, I don't know, maybe about right there. And if I do it again, maybe about right. Did everybody see what I just did? I just found a couple places on this graph where the tangent lines were parallel to the secant line. Okay? First of all, how did I know it was even possible? So this is the conditions. As long as my function is differentiable, last day it only had to be continuous. Now it actually has to be differentiable, which means I can't have any cusps, corners, weirdnesses going on in the interval. And it has to be a closed interval. If I have a closed interval that's differentiable everywhere in between, then it means there's at least one place in this interval where the slope of the tangent line is the same as the slope of the secant line. That's why the lines would be parallel, because they have the same slope. Okay? You with me so far? So that's not really a stretch, is it? So if you just drew anything on a piece of paper, you know, let me just draw just a simple, you know, from here to here. Okay, great. I'm guessing maybe about right there. It's pretty easy to see that I could always do this. Oh, that's not going to work. Why? Because that's not differentiable. Right? I drew a cusp. Oh, as long as it's differentiable. This is continuous, but it's not differentiable. It has to be differentiable, meaning the derivative has to exist at every point. So there can't be a cusp, a corner, a vertical tangent, any weirdness is going on. It's got to be a happy, let's say, boring curve. But if that's the case, I can do this. So now we'll state the theorem. Okay? Okay. If f of x is differentiable, I just sometimes say diffable, over the interval a to b, I can only talk about differentiable over an open interval, and now we're going to do like we did last day. Now we're going to fill in the endpoints. Okay? Comma. The limit as x approaches a from the right of f of x is exactly f of a the limit as x approaches b from the left of f of x is f of b. So what I really did was I started with this, and then I filled in the endpoints. And the endpoints were exactly where they were supposed to be. And I'll show you examples of why that's so important. My original function might have an endpoint, like the square root function. This just says, as long as I'm looking at the open interval and everything's cool, and now I fill in the endpoint, it can be the endpoint of the function, like the square root is. Okay? Then there exists a c in the interval. There exists a value in the interval, a number. Such that f prime of c, that would be the slope of the tangent line evaluated exactly at that number. I'll give you a hint. See this guy here? That's c. Is equal to the slope of the secant line, which would simply be f of b minus f of a over b minus a. I mean, literally your rise over rho. Change in y over change in x. So I'm giving you a closed interval. I need a closed interval so I have endpoints, because these are the endpoints, aren't they? I'm finding the slope of the secant line. That's easy. That's not calculus. That's literally pre-algebra. I'm taking the derivative, and I'm finding the one value. Oh, by the way, in my picture, there's more than one value. Mean value theorem guarantees a value. But I could have more than one. How could I possibly have more than one value? I could have infinitely many values. Oh, I just am guaranteeing you one. That's good enough. But I could have many. In this picture, I got one. If I'm turning around several times, I might have several times. I'm just guaranteeing you the one. As long as I'm differentiable, that is the key. I got to be differentiable. So let's do an example of this. It's a theorem that by itself we don't really have a lot of use for. We're not going to answer big questions right now. It's a building block for a bigger theorem and other bigger theorems that you're going to learn later on. Okay? So let's consider the following. All right? So first of all, we want to determine if the mean value theorem, that's what this is called, is satisfied for f of x equals the square root of x over, let's say, 1 to 9. If it is, find c so that f prime of c equals f of 9 minus f of 1 over 9 minus 1. There's my a and my b, in other words. So the first thing is we have to determine if the mean value theorem is satisfied. Or I should say, sorry, if the hypothesis, sorry about that, hypothesis. The hypothesis, all theorems say, if the following is true, then this will be my guarantee. If the hypothesis is satisfied, then the conclusion is guaranteed. That's how most theorems start. So the hypothesis is that I have a function that is differentiable over this interval and then over the open interval and the endpoints exist. Is the square root function differentiable everywhere? Certainly not to the left of 0, not even at 0. But where am I going? 1 to 9. So is that a good interval to use? Yes. So we can say, here's the first thing we're going to say. F of x equal root x is, I'm going to abbreviate, differentiable over 1, 9, and the endpoints exist. I have satisfied the hypothesis. Because I've satisfied the hypothesis, the conclusion is now guaranteed. Okay? So I need to do two different algebraic pieces. I need to find the slope of the secant line, and I need to take a derivative and then set them equal. So let's do the easy one. F of 9 minus f of 1 over 9 minus 1 equals the square root of 9 minus the square root of 1 over 9 minus 1. What will that give me? So 3 minus 1 over 9 minus 1 is?
1.
So 1 over 4? Everybody agree with that? Okay. What is f prime of x? One over 2 root x. So here's what I want to do. F prime of c is 1 over 2 root c, and I need that to equal 1/4. If you just left it as an x, that's fine too. Most textbooks like you to use a specific value there. Can you solve this for me? 4? Are you waving at me?
4.
4, okay. Well, it says c equals 4. Do you guys agree with that?
Yes.
Now, something important here. Where does that 4 have to live? That 4's got to live in this interval, does it? Yeah. Right? We celebrate, we rejoice. We only got 1, but we got an answer. So the mean value theorem, because the hypothesis was satisfied, the conclusion was guaranteed. So if we drew a graph of what we just found, right? Here's a square root function. I used, here's 1, 1, and here's, let's say, 9, 3. Oh, no, might as well use my, I've got all this advanced technology, I might as well use it, right? Can't draw line segments very well. All right. There's my secant line. This line has a slope of 1/4. We said when, see that's 1, right? You know, that's 9. Don't worry about accuracy of scale. So we're saying there's another place on here, namely at 4. It's kind of what we just said. At x equal 4, the tangent line has the same slope as the secant line, meaning they're parallel. That wasn't too hard, was it? So that really is not too bad at all. All right, let's try another one. All right, so let's do same question. This time we'll use f of x, keep it simple. We use f of x as x squared, and we'll use the interval from, how about -1 to 4. So the same question. This is, technically it's a monomial, but it's part of a polynomial. Polynomials are continuous and differentiable everywhere. So this is differentiable over the entire number line, agreed? So does it satisfy the hypothesis? Yeah, you couldn't get any better than polynomials. So this satisfies the hypothesis of the mean value theorem, so now we can go ahead and find a real number between -1 and 4 that makes this true. But now, I'm going to do it the other way around. I'm going to draw the picture first. We know we can answer this question. So I've got, here's one point. And the other one, don't worry about yet, accuracy of scale. Way, way up here, okay? So maybe it's right there. Now, when I'm looking at this, assuming I've done this sort of accurately, okay? Do you agree that somewhere out here I ought to get an answer? Maybe somewhere in here?
Mm-hmm.
I mean, I can clearly see that. I mean, I don't want to eye shot it, but it's really not that hard to see that there's going to be a place where I'm going to get a parallel line. Okay? I'm pretty sure our conclusion is going to occur. I don't know where it's going to occur. I actually have to calculate that. But I'm pretty sure I'm going to be able to find an answer. So let's do that. So let's start with f of 4 minus f of negative 1 over 4 minus negative 1. Well, what's f of 4?
16.
What's f of negative 1?
1.
And what's 4 minus negative 1? 3. Okay. What is f prime of x?
2x.
Just 2x? So I want 2c to equal 3. I think I can handle this one on my own. 3 halves? That was 4, so we're about right here. You know, my free-handed line, that's not too bad, right? Not too bad at all. For next value of 3 halves, I got the exact same slope as I did on the secant line. Do you ever have to draw the picture in order to answer the question? No, we answered the question over here. So that was fairly simple stuff. Okay, let's do another one. All right. All right, let's do f of x equals 1 over x, and we'll make our interval negative 1 to, I don't know, 3. Simple, not too complicated. All right, so I'll do the same thing I just did there. Well, actually, no, let's go ahead and do the derivative first. We'll do the derivative first this time. So that's going to be what?
Negative 1 over x squared.
Okay, and now I need f of 3 minus f of negative 1 over 3 minus negative 1. Be sure I subtract correctly. Well, f of 3 would be a third. F of negative 1 would be negative 1, right? And on the bottom I'd have a 4. So 1 minus, did I do that right? Yeah, 1 minus negative 1 would be, or 1/3 minus negative 1 would be a third plus 1, or 4/3. So this is 4/3 over 4, that's just 1/3. Okay, so now I need to solve, I need to say, okay, f prime of c, which is negative 1 over c squared, I need that to equal 1/3. That would mean that c squared needs to equal negative 3. Houston, we have a problem. It's not working. Did we make a mistake? I mean, I don't think we made an algebra mistake. You know, let's draw a picture. Why don't we draw a picture? It's got to be worth at least, I don't know, 1,000 words, right? So I used negative 1, 1, and I used 3, 1/3, and then I said, there's my secant. And when I took my rolling ruler, it's never going to work, is it?
There's a separation.
What's wrong?
It's outside of the interval.
Well, am I differentiable over this whole interval? I'm not even continuous over this whole interval because of I have a vertical asymptote smack dab in the middle of my interval. Oh, we didn't satisfy the hypothesis of the mean value theorem, therefore the conclusion didn't happen in this case. By the way, if you don't satisfy the hypothesis, all bets are off. It is possible the conclusion could still happen. No, it's if you satisfy the hypothesis, the conclusion is guaranteed. I did not satisfy the hypothesis and the conclusion didn't happen. There is no place where, right? In fact, all of the tangent lines are going to have negative slopes here, aren't they? All the tangent lines here are going to have negative slopes, but that's positive. That's not going to work because we didn't satisfy the hypothesis. That's why this didn't work. Okay, I kind of went fast on purpose. Like, wait a minute, but now, can I change this problem so it does work? Yeah, I'm going to change one thing. Does this satisfy the hypothesis of the mean value theorem? This function is differentiable for all real numbers except zero. And as long as my interval did not include 0, it does satisfy the hypothesis. This is okay. So how does that change? Because I said now let's use positive 1. That's why it's so important that I'm being aware of what it is that I'm working with. What is the theorem? That's now a 1. So now my numerator is negative 2/3 over 4. That's negative 1/6. Oh, that's different because I'm also not using that. I now went from here to here. Now, I didn't give you much separation, so this will be a little harder to see. Do you think if I go down just a little bit, I'll have a parallel line on a tangent line? I think we can all see that, yeah, I can clearly clip something between these two. Okay? So now what am I setting equal? Not 1/3. Negative 1/6. So I need c squared to equal positive 6. Now, there are two values. C is negative root 6 or C is positive root 6. Do I consider both of these? Root 6 is close to 2.5.
Negative.
2.5 is in that interval, correct? But is negative root 6 in the interval? No, so we just go like this. We did something similar to this when we did extreme value theorem. We found all of our critical values, and if we had a critical value that wasn't in the preset interval, then we just cross it off saying it's extraneous. This is a solution to this equation, but it does not answer this question because it's not in that interval. That's why we throw it out. So the slope of the tangent line when x is positive root 6, which is definitely between 1 and 3, the slope of that tangent line will be the same as the slope of the secant line. Okay, question?
What did it change the first, instead of 4, what did it be 2? On the...
Oh. Yes, you're right. Hold on. No, you're absolutely correct. Where did it, we didn't finish this one, did we? That should be a 2. Okay, it changes this a little bit. So what is that now? That's a 2. So this is negative 1/3. So that's a 3. Okay. Let me change these to 3s. I'm glad you caught that. 3 is, the square root of 3 is like 1.7 something. It's still between 1 and 3, isn't it? That is very important. That was a good catch because that was an error. We're still going to be okay though, aren't we? If this put us outside, then we're in trouble. So again, if the hypothesis is satisfied, the conclusion is guaranteed. For those of you who have ever had any formal logic, a conditional statement, if then, if A then B, or A implies B, says if A occurs, then B is guaranteed. You know, if a polygon is a square, then it is a rectangle. Is that a true statement?
Oh, polygon is a square then. Yes.
If it's a square, then it is a rectangle.
Yes.
Yes. If it's a rectangle, then it is a square. No, not true. That's called the converse, if I do it in reverse. If I understand basic logic, if A implies B, then not B implies not A. If we score more points, then we will win the game. We did not win the game. We did not score more points. That's safe to say. If you score above 90% in this class, you will get an A. You did not get an A. You did not score above 90. Now, if you score above 90, you get an A. What if you don't score above 90? Does that mean you can't get an A? Well, maybe you nailed the final exam. Maybe there might be another path. It's just that if the hypothesis isn't satisfied, the conclusion is not guaranteed. It doesn't mean the conclusion cannot happen. It just means the conclusion is no longer guaranteed. How many have ever worked with truth tables? You know, true, false. In a truth table, right? True, 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 false, false, true, false, false. One of them we say is a lie. The condition, the hypothesis was satisfied, it was a true, but the conclusion was not, it was a false. But what if the hypothesis is not satisfied? You got a false, but the conclusion still happened. You didn't lie. You just can't guarantee the conclusion if the hypothesis doesn't happen. So that's what we understand. If we score more points, then we win the game. We did not score more points. The other team didn't show up. Can we still win the game? Yeah, but I can't guarantee that. If we score more points, I can guarantee we win the game, but maybe we won because they didn't show up. There are situations that if the hypothesis isn't satisfied, the conclusion might happen, but it's not guaranteed. So I don't even want to go there. I don't even want to deal with it. I only want to deal with the absolute guarantees. Most theorems are in an if-then state, or they're in an if and only if, called a biconditional. If A, then B, and also B implies A. Works in both directions. We don't get a lot of those. We like those. Now, I'm going to tell you about a situation. I've been teaching this for about 1 million years. And this one is going to keep you awake at night, by the way. All right? Many, many, many years ago, I had a roommate. We were friends for a while. And I think he ended up becoming a lawyer because he loved to argue. That was his favorite thing on planet Earth. He would argue, and in his mind, he won all arguments because you would just give up because his arguments were just so dumb after a while, or he'd just be so loud, you just like, I'm not even going to bother. So in his mind, he'd win all arguments. So he had a sports car, and he really liked driving fast. But he liked driving fast in the wrong places, like neighborhoods, things like that. So one particular day, I want to say it's like in the La Jolla neighborhood, he was going, well, let's just say really fast. Like, 80 in a 15 or 20 zone, and he's pulled over. And the officer's being particularly kind because he knows technically he can arrest him and put him in jail for driving that far over the speed limit. So he put a lesser number down, but it was going to be a very expensive ticket. And he writes it up. So my friend decides he's going to challenge this. I don't know if any of you have ever been to traffic court, but I mean, it can be endless, and the cop may or may not show up, but it doesn't matter. But my friend went and he defended himself, and he made charts and graphs and pictures, and he had some of them professionally done to illustrate his point. So here's the point. The officer, I think, wrote him up for maybe going 60 instead of 80. So my friend said, the cop wrote me up because he said my average speed was 60 miles an hour, but I maintain I was never actually traveling 60 miles an hour. Therefore, the ticket is null and void. And he had all sorts of charts and graphs. He was asking my opinion, and I said, no, you can't win. This is impossible. So he argued and kept referring to his charts and graphs, and the judge dismissed it. This is a mean value theorem question, just so you know. He's starting from a dead stop. He told me he might have gotten actually up to 100 miles an hour. He just wanted to see if he could. Cop wrote him up for his average speed being 60 miles an hour. He said he was never actually going 60 miles an hour. Is that possible?
For a second, he was.
You're driving up to LA, and only in Southern California, when we say how far away is it, do you give an answer in time? Because we know distances change in Southern California. Well, how far is it? It's about 3 hours away. You laugh about it, but no, I'm from Northern California, and we actually gave distances in distance. And so I had to learn that distance is meaningless in Southern California. It's always based on time. So if I say, how far is it to LA? Well, it's 2 hours depending on traffic. So the distance to LA is different depending on traffic, is what we always say. Okay, so you went to LA, there was nobody on the road, it took you 2 hours to go 120 miles. Your average speed was 60 miles an hour. Does that mean you drove 60 miles an hour the entire duration of the trip? Well, that's not possible because you had to start from a dead stop and you had to come back to a dead stop. Okay, so you went from dead stop to 60 back to dead stop. Would your average be 60? It'd be a little less than 60. Didn't you have to pass through 60 at some point if your average was 60? This is mean value theorem. Here's what we do know is an absolute. Motion is always differentiable. So, I'm going to draw the picture that I was trying to explain to my friend. This is you stopped. This is distance. This is time. Dead stop, sped up fastest, slow down, came to a stop. What is the officer saying the slope of that line is? 60. Is it possible that he was never going 60 miles an hour at any point?
Mm-mm.
Is that possible? Or did he have to be going 60 at least 2 times? One on the way up and one on the way down, especially if he said he was at one point way over 60. Yeah. Now, is it possible he was never going 60 only if the motion is not differentiable? Like if I had a cusp. Remember I drew one earlier with a cusp. So this is the way, so this will keep you up. Every class I've ever taught, I've showed them this and I help people say they can't sleep for the next week because they're thinking of all the scenarios. Like I'm driving along and then the helicopter came and picked up my car and then quickly went. You still sped up. I mean, I was going and then the Starship Enterprise beamed me over to. I guess that would not be differentiable motion in a sense, but people will be thinking of every scenario that could exist that would not. And if you come up with one, let me know because I've been teaching this example since the 80s, and no one's come up with an example. No, according to the mean value theorem, he had to have been going 60 at least once, probably twice, because when the cop pulled him over, So the question begs is, why did the judge throw it out?
Judge was annoyed.
I think it's like, how much longer do I have to endure this argument? I have a feeling literally the judge threw in the towel at some point because when my friend, we were roommates at the time, he came back and said, he threw it out, like, there is no way. There is no way. And he was showing me his charts and graphs, and they're all very mathy and completely wrong, by the way. And he had non-differentiable motion on his things because he talked to somebody, I think, who knew physics and said, well, here's how it could work. And, this is a classic problem. So here's where mean value theorem would tell you, no, you had to have been going that fast. Now, has anybody here, again, you're not turning yourself in, but let's say you're driving in Northern California, like on I-5, where it's endless. And you have those, you guys know what I'm talking about? You'll have they'll call them speedometer checks. Mm-hmm. You'll see 1 mile, 2 mile, 3 mile, 4 mile, 5 mile. How many know what I'm talking about? They usually on long stretches of freeways. I learned years ago those aren't speedometer checks at all. They're not even like speedometer checks. They're for the planes that are flying overhead to determine if you're speeding or not. It's real simple. They see you when you pass the 1 mile mark. They time how long it took you to get to the 2 mile mark. It takes about 2 seconds on their onboard computers to say what was your average speed. And if the average speed was too fast, they'll then radio down to a car and they will pull you over and give you a speeding ticket. They tell you those are for speedometer checks, to check your odometer, speedometer. Because if you went through that 5 miles and it didn't say exactly 5 miles, let's say it said less than 5 miles. Do you know what that generally means? Your tires. They're too big or too small. And now that affects your speedometer because it's based on the revolutions of the tires. By the way, that is a problem. I had that happen once many years ago. I put tires on my car that were, I think, 1 inch too big. So the car said I was going slower than they actually was. And I got pulled over one time for going, 3 or 4 miles an hour over the speed limit, but I thought I was going exactly the speed limit. And then the officer explained to me, said, well, this is why, because your tires are too big. He didn't write me a ticket, fortunately. But I had to swap out. So that can be a thing. So what they're doing, they're not finding your instantaneous rate of change. You'd need a speed gun for that. They're just basically timing you how long it took you. And it's obvious when they're overhead and they see that one car, zipping past all the other cars. It's not really hard. Okay, they made that mile in 36 seconds. You're probably going really fast. And so then they'll radio down. I learned this years ago from a highway patrolman. That's what those are for. Oh, it's nice that you can check your own speedometer, but it's for their convenience. But they're giving you the average. So is it possible for you to have an average that's too fast without ever breaking the speed limit? If they're saying your average is 75 and you're in the 65 zone, Then you had to be going at least 75 for part of it, right? Probably faster. Maybe you're in cruise control, you went 75 the whole time. Either way, you lose, don't you? You're not winning that argument. The only way is if maybe you started from a dead start, or you stopped your car really quickly before you got to the end and now it took you too long to get to the next mile marker. Probably not happening. But this is actually the mean value theorem in practicality. We use that in terms of simply in describing motion. It actually is very effective. When you have physics next semester, you will use this at a low level to answer simple questions like that. Okay? Any question on this? Yeah, this is not supposed to be challenging. Where a lot of folks make the mistake, though, I'm going to ask, does something satisfy the hypothesis? The hypothesis is that you are differentiable over the interval. And if you're not, the conclusion may not be guaranteed. But if you are, you need to state, yes, it's a polynomial, it's differentiable over the whole number line. It's the square root function is differentiable for all positive numbers. It's a sine wave, whole number line again. Right, square root function, like I said, positive numbers. The 1 over x, differentiable for all negatives or all positives. But you have to have separate, but you've got to make that statement because without that, there's no guarantee of the conclusion. That's the easy part. You're not proving anything, you're just stating a fact that now will allow you to finish the problem. But the most important thing is whatever you give as an answer, that answer's got to be in the interval. So if you have a situation where you got 2 answers or more, just take whatever answer or answers are in the interval. It's possible you could get more than one. But if your only answer is outside the interval, that's a problem because that means you didn't satisfy the conclusion. So then you got to go back and recheck. Okay, let's go ahead and stop that. Question?